Hi, it's Yohei Kawasaki. My research topic is identification and authentication using Clavicles. Neck-mounted devices have become popular. These include wireless earphones, speakers, as well as assistive devices for various tasks. In the future, it is believed that neck-mounted devices will require functions for identification and authentication. Specifically, there are three scenarios. Firstly, in the context of being used as mobile devices, anticipating that wireless earphones will become like current smartphones in popularity and usage. There may be situations where access to highly confidential information is needed. This underscores the need to authenticate the user. Secondly, the prevention of impersonation and interception is crucial. For instance, in scenarios like remote work, there's a need to constantly authenticate the user to prevent thief and eavesdropping of wireless earphones by third party. Third, there's a scene of utilizing wireless earphones as shared devices. For example, in cases where wireless speakers are shared with a family and identifying the user allows for content recommendations. This study focuses on neck-mounted wireless earphones and aims to develop an identification and authentication system. Focus on the fact that the device is touching the clavicle. This study implemented a system using the acoustic features of the clavicle. Here is a related research. Two major types of methods exist for acoustic sensing. The first is a passive acoustic sensing, in which a microphone is used to sense the sound that occurs naturally when an object is touched, and the sound is analyzed to obtain acoustic features. For example, a glass plate is equipped with microphone, and the sensor values of each microphone when the glass plate is touched are used to estimate where the object is touched. There are also studies that use gestures of the teeth. On the other hand, active acoustic sensing involves the use of a vibrator to generate vibration in addition to a microphone. By sensing the acoustic features of an object using this method, there are studies that estimate grasping posture and hand posture. Here is an explanation of the principle of active acoustic sensing. Active acoustic sensing is a method of measuring the acoustic properties of an object and it's implemented using a vibrator and a microphone. First, a vibrator and a microphone are placed on the object whose acoustic properties are to be measured. Next, vibrator generates vibrations which are propagated into the object. The propagated vibration is sensed using a microphone, and the acoustic properties are obtained by analyzing this signal. This is the principle of acoustic sensing. In this research, the object is in this figure is clavicle. Studies have been conducted to identify and authenticate individuals using the acoustic properties of bone, some using skull, bone, and wrist bone. These studies have used active acoustic sensing to measure the acoustic properties of bones, but as far as I know, there have been no studies using the acoustic properties of the clavicle. Research has been conducted on identification and authentication on hearing devices, but most of the research has been based on the use of individual differences in ear acoustics. They are dependent on the ear internal environment, and it is difficult to standardize the angle and position of the ear each time the clavicle device is blown. There are three main types of authentication. The first is knowledge-based authentication, which involves the risk of forgetting or leaking them. The second is position-based authentication, which involves the risk of ghost or thief. The third is biometric authentication. There are two main types of biometrics. One is based on physical features such as iris and fingerprint, which is unchanged throughout life, and the other is based on behavioral features such as gait and handwriting, which express habits and tendencies. The acoustic properties of the clavicle are physical features in this study. Next, this section is the difference between identification and authentication. Although at first glance the words are similar, the tasks and evaluation index are different for each. In identification, the task is to determine which class the input is. In authentication, the task is to determine whether the input is the person's data. In identification, the evaluation index is accuracy. In authentication, the evaluation index is equivalent error rate. For identification, the process involves using a pre-trained model to calculate and estimate the class to which the input data belongs. For authentication, the procedure involves calculating the similarity between the input data and the data set of the target user. In this context, let's determine the target user as user A, and let's calculate similarity as S. When a threshold is set, if S is below or equal to the threshold, the input data is estimated to belonging to user A's dataset. Conversely, if S is greater than the threshold, it is estimated that the input data does not belong to user A's dataset. As a result, there can be cases where one self's data is considered as others, and this rate is called the false rejection rate. Conversely, there can also be cases where others' data is considered as oneself's. This rate is called the false acceptance rate. These rates change based on threshold. A lower threshold leads to higher FRR, while a higher threshold leads to higher FAR. As illustrated on the right, there is a trade-off relationship between the FRR and the FAR. The equal error rate refers to the point where these two rates match when the threshold is valid. The experimental setup is shown in this figure. And here is a figure of the device being attached for use in experiment. This is an analyze overview. The obtained sensor values are converted to a frequency spectrum and they are converted to a Mel spectrum. Finally, it is converted to Mel frequency spectrum coefficients. The Mel spectrum was used as a feature for identification, and the MLCC was used for authentication. The vibrator is placed on the left clavicle and the piezo microphone on the right clavicle. The vibrator generated a signal, and the piezo microphone measured its vibration for 2 power 18 frames at 96 sound Hz. By performing the trained window function processing and fast Fourier transform on the sensor values, and 2 power 18 frames of data are converted into 2 power 70 frequency spectrum. The obtained frequency spectrum was transformed into 100 spectra by processing with a metadata bank. A discrete cosine transform was applied to the obtained Mel spectrum and the MFCC was extracted. 12 low frequency components were extracted as features. The model was evaluated by tenfold cross-validation. For identification, we used random forest for the classifier and Mel spectrum for the features. For authentication, Mahalanobis distance was used for similarity calculation, and MCC was used for features. Next is about an experiment. We prepared white noise and pink noise as signal. Each participant measured the acoustic features 50 times per signal. The participants asked to put on and take off the device for each measurement and to wear a cotton t-shirt in common. The participants were 5 males. Here is identification result. 97.6% for white noise and 98.8% for pink noise. Here is the authentication result. 4% for white noise and 4.8% for pink noise. Finally, there are limitations and future work. As for limitations, the participants were asked to not to speak or move their bodies. There are also limitations such as the vibration sound can be heard. For future work, we are considering expanding the number of subjects. We are also considering experiments that take into account changes in posture, differences in gender and body size, and the effect of clothing in order to improve robustness. This is summary. Thank you for listening.